Hi, everyone, and welcome to JuliaCon 2020. So this is our first fully virtual JuliaCon. And the last time I checked, we had about 10,000 people that were registered, which is huge for us. And this means that we have more people than ever to thank. First off, our attendees make this event what it is by tuning in and bringing your enthusiasm. We also have a fantastic organizing committee that this year especially had to meet some new challenges to make this event online. Similarly, our presenters dealt with some unusual demands. For example, some of them presenting workshops live at odd hours or in the middle of the night to accommodate our conference agenda. Finally, we do have expenses even for an online event. So we'd especially like to thank our sponsors for sticking by us even during the pandemic. Their participation makes it possible for this event to be free for all of you tuning in. So in particular, thank you to our gold level sponsors, the Moore Foundation and Julia Computing. And thank you to our silver level sponsors, Invinia, Jeffrey Sarnoff, JustPay, Pumas, Zapata, and Repl IT. Additionally, we have a few media partners this year, Pact, Sticker Mule, and Vercel. And NumFocus continues to be our fiscal sponsor for the Julia project. So thank you again to all of you. And with that, I give you Professor Karen Wilcox, our first keynote speaker.
Jane, sorry, I think I started 5 minutes before time. So
okay.
We may want to wait a couple of minutes and then start again. We are still streaming, but
okay.
We just wait for people to join. Sorry about that.
Okay, okay, sounds good.
You can call that a practice run and do it again, although it was already perfect.
It was a practice run.
But now if I say exactly the same words, well, and I'm saying this live, but I always like draft what I'm saying so that I don't freak out and blank out when, when I'm streaming.
We'll edit it.
Yeah.
We were supposed to start at 20 past the hour. So, but I kicked off at 15 past the hour. Sorry, too excited.
I knew there was some sort of lag on YouTube, and 5 minutes seemed kind of large, but I trusted you.
Sorry, too little sleep in the last week.
I can't imagine why.
Okay, another couple of minutes and then we'll get going.
Okay.
You realize why radio and TV hate dead time is the worst thing for everything when you're doing live stuff. Just another minute, and then we'll get started.
And we should have prepared some sort of like Julia animation for these moments.
Yeah, I know. Well, next year.
Yeah.
Yeah, like a transition. Or
I think it's time.
All right. Yeah. Okay. So hi again, everyone, and welcome to JuliaCon 2020. This is our first fully virtual JuliaCon. And we have about 10,000 people registered so far, which makes this a huge conference for us. And it means that we have more people than ever before to thank. First off, we're really grateful to have all of you tuning in, joining us today. Our attendees really make this event what it is by bringing their enthusiasm. We also have a fantastic organizing committee, and especially this year, they had to meet some new challenges to take the event online. Similarly, our presenters dealt with some unusual demands. For example, some of them had to wake up in the middle of the night to present live workshops at odd hours to accommodate the conference schedule. Finally, we do have expenses even for an online event. So we'd especially like to thank our sponsors for sticking by us even throughout the pandemic. Their participation made it possible for us to make this event free to everybody who wanted to join us. In particular, we'd like to thank our gold level sponsors, so the Moore Foundation and Julia Computing. We'd like to thank our silver level sponsors, Invinia, Jeffrey Sarnoff, JustPay, Pumas, Zapata, and Repl IT. And then our media partners, Pact, Sticker Mule, and Vercel. And finally, our fiscal sponsor for the Julia project, NumFocus. So thank you again to all of you. And with that, we'll turn it over to Professor Karen Wilcox, who is our first keynote speaker for JuliaCon 2020.
Great. Thank you very much, Jane. And it's great to be joining everybody here virtually today, although I'm sure we all wish we were in Lisbon right now. So today I want to share some thoughts on scientific machine learning, which is certainly a topic that's of interest to many people today. Before I start, let me get control back of my computer, there we go. Before I start, let me acknowledge the folks who have contributed to the work that you're going to see today. Dr. Cheng Huang, who is a research engineer at University of Michigan, who we collaborate with on the combustion work. Boris Kramer is a former postdoc of mine who's now assistant professor at UC San Diego. Shane Macquarie is one of my current PhD students in computational science, engineering, and mathematics at the Odin Institute. Elizabeth Chan is one of my PhD students in computational science and engineering at MIT. Benjamin Peerstoffer, another former postdoc who's now assistant professor at Courant, and Renee Swischuk, a former master's student from MIT who is now in industry. So today I want to touch on three things. First of all, scientific machine learning. What is it? Why is it so exciting? And how does it manifest as methods, algorithms, and implementations? Then second, I want to dive in a little bit more deeply to some of the work that we're doing that falls into the realm of scientific machine learning, and specifically learning predictive models through the lens of projection-based model reduction. And then third, I'll close with a brief outlook. So scientific machine learning, as I mentioned, it's a topic that is receiving a lot of attention. It's a very exciting topic. And of course, it's also a topic that's very relevant to Julia. And it was really great to see the workshop on scientific machine learning offered on Sunday, and many of the talks touching on this topic throughout JuliaCon. So one set of context of the challenges and the opportunities for scientific machine learning can be found in the report, whose cover I'm showing here. This is a report written by a working group of which I was a member, and that working group was commissioned by the Department of Energy Advanced Scientific Computing Research Program. The report was released in February of last year. So quoting from the report, scientific machine learning, or SciML, is a core component of AI and a computational technology that can be trained with scientific data to augment or automate human skills. Across the DOE, SciML has the potential to transform science and energy research. Breakthroughs and major progress will be enabled by harnessing DOE investments in massive data from scientific user facilities, software for predictive models and algorithms, high-performance computing platforms, and the national workforce. Now, while that is clearly very focused on the Department of Energy, I think we can look at this context and see opportunities much more broadly, and also see the pieces that really need to come together for scientific machine learning: the data, the scientific data, the software, predictive models and algorithms, high-performance computing, and then, of course, the people. So as I think about scientific machine learning and try to frame the field, really, to me, the question that I'm showing here sits at the heart, which is what are the opportunities and challenges of machine learning in complex applications across science, engineering, and medicine, and in particular, complex applications that have traditionally been the domain of physics-based models of computational science. So as we look at this question, we see there are two parts, the opportunities and the challenges. So in terms of the opportunities, clearly it's very exciting to think about very challenging applications in science, engineering, and in medicine, and to ask the question, how do we do better? How do we bring new methods from machine learning, and not just new methods, but new ways of thinking about problems, new ways of harnessing the data to drive better predictions and better decisions ultimately. So clearly the opportunities are huge. But what are the challenges? And in particular, what is it about complex applications in science, engineering, and medicine that is different and that is hard, and that means we cannot just take methods of machine learning that exist today or methods that are developed for other fields and just wrap them around blindly around our applications. So there's clearly a big opportunity, but there are also big challenges because these problems are different. And as we think about those opportunities and challenges, there are a number of elements we need to keep in mind, and I show 5 of them here. The first is the notion of respecting physical constraints. So this is a recognition that when we talk about complex applications in science, engineering, and medicine, we're often talking about problems that have physical constraints, have governing laws, laws of nature that come along with them. And the question of how or whether one respects physical constraints feeds into both the opportunity and to the challenge. It's a challenge because we have to craft scientific machine learning methods that will incorporate physical constraints, but it's also an opportunity because it's the very nature of those physical constraints, the governing laws, the physics-based models, the very nature of those that actually bring structure to otherwise completely hopeless problems, bring structure and let us craft computational algorithms that can make these very complicated problems tractable. So this first one is very key, but again, I want to emphasize it's not just about making sure machine learning respects physical constraints. It's about using the physical constraints to drive a new generation of methods and algorithms that exploit structure and that become tractable in very, very complex situations. Second, we have to think about embedding domain knowledge, and of course this is a challenge for machine learning in any application, but thinking about how we build on decades, if not centuries, of domain knowledge that has been accumulated across science, engineering, and medicine. And again, often that domain knowledge comes to us in the form of models. And a related challenge, which is bringing interpretability to the results. So again, recognizing that with these complex applications comes really critical predictions and decisions that literally impact people's lives, that impact everything about society. And with the current pandemic situation and the use of predictive models to guide policy, we really see that at the forefront. So bringing interpretability to results, being able to explain results, understand why various predictions are being made, and also to understand how good they are, and on the flip side of that, just how wrong they might be. Fourth are the challenges around data. Again, managing data is a challenge no matter what the application of machine learning. When it comes to science, engineering, and medicine, we are dealing with heterogeneous data that come from many different sources. The data are often noisy, and really importantly, there may be a lot of data, but the data are often sparse and incomplete. The reality is that when you're in the physical world, the physical or natural world, it's practically impossible to sense everything about the system. So we're dealing with sparse, incomplete, and indirect data, and that in itself creates a large number of challenges. And then finally, and I already alluded to this a little when I talked about interpretability, so much of what we do in science, engineering, and medicine is about trying to predict the future, trying to predict what will happen if we design a system a certain way, what will happen if we use a particular medical intervention, what will happen as the climate dynamics evolve into the future. And that those predictions are by necessarily going to be imperfect, whether it's data or models or the two together. Our decision-making will be imperfect. So the need to quantify uncertainties, understand where uncertainty feeds into the system, and nonetheless make predictions, make decisions while accommodating risk is also a significant element. So framing and thinking about both the challenges and the opportunities, I think that at the heart of overcoming these challenges of scientific machine learning is a need to recognize that big data alone is not going to be enough. It's really critical that we combine data-driven learning with physics-based modeling, and it's by putting these two together, it's the only way that we're going to break the barriers of complexity. So what do physics-based models bring? They bring predictive power. As I already mentioned, they let us simulate what-if scenarios. They let us learn about our system's behavior without ever having to let the physical system or wait for the physical system to get into that state. That predictive power is so critically important. They also bring interpretability, and a physics-based model is often what encodes domain knowledge. So when we talk about incorporating physics-based models, we're no longer in the realm of computer science. We're now in the field of computational science, or computational science and engineering, CS&E. So computational science, or CS&E, is an interdisciplinary field that uses mathematical modeling and advanced computing to understand and solve complex problems. At its core, CS&E involves developing models and simulations to understand physical natural systems. So again, sort of looking at that definition and thinking what is computational science, what we see is this notion of a mathematical model encoding information about a physical or natural system. That's what sits at the heart of computational science. So when we say scientific machine learning needs to incorporate physics-based models, it's not just the models themselves. What we really mean is we need scientific machine learning to incorporate all the computational science machinery that is what lets us deal with those models and which is what makes those problems tractable. So scientific machine learning must fundamentally embed the foundations of computational science. And of course, this is highly relevant to JuliaCon, with Julia being one of the programming workhorses that does exactly that, lets researchers and those out in the field build the software implementations of those foundations. So I want to dig in just one level deeper to some of the challenges of complex problems. And remember, I'm talking about complex problems across science, engineering, and medicine, and thinking about what is it that computational science brings in terms of foundations to tackle those problems. So the first one is that these problems tend to be described by complex, multi-scale, multi-physics phenomena. And more often than not, the models come to us in the form of nonlinear systems of partial differential equations or large systems of ordinary differential equations. Why is it so relevant that the phenomena are complex and multi-scale, multi-physics? Because for systems with this complex behavior, what we know is that if you change the parameters just a little, change the geometry of a system, change the boundary conditions, change the forcing, you can see very drastic changes in the behavior of the system. And what's more, that kind of sensitivity to the underlying parameters is most heightened when a system is in a condition such as being close to a failure boundary or close to an instability. And those are the conditions that are most important for us to understand and to be able to predict as we drive forward with decisions around these systems. So computational science has, of course, considered this challenge, and certainly there are still many open challenges, but through decades of advances in discretization methods and solvers that recognize and embrace the multi-scale, multi-physics nature of the problem and exploit the structure to again, make those problems tractable. The second significant challenge is the dimensionality. So again, if we're talking partial differential equations, the parameters are often going to come to us in the form of infinite dimensional fields. If we discretize those fields, we're not talking hundreds or thousands of parameters, but we are talking problems with millions or billions of parameters. And so viewing those problems simply through the lens of data and sampling is clearly going to be intractable. Instead, computational science builds scalable foundations, methods such as adjoint methods that let you compute sensitivities of complex systems in a very efficient, scalable way. Algorithms that, again, exploit the structure, whether it's through multi-grid or multi-level approximations, or through the information, the low-rank information that might be embedded in a Hessian. Methods such as model reduction, sparse grids, and the list goes on and on. But again, this challenge of high dimensionality and breaking down the complexity associated with high dimensionality sits at the heart of much of computational science. Third, I wanted to reinforce a point I made earlier about the data, which is when we're talking science, engineering, and medicine, more often than not, the data are sparse. And it's not just a matter of saying, let's get more data, because the data are intrusive and expensive to acquire. It may be physical sensors in the physical or natural world. It may be intrusive tests on a human patient. So we have to live in a world where data will be sparse and indirect. And what that translates to is ill-posed inverse problems, first of all, which, again, inverse theory has a long history in computational science with both theory and scalable algorithms. And then second, a need to think about optimal experimental design. What is the best use of our resources to acquire the data that will best inform a prediction or a decision that we need to make? Fourth is we need to be very cognizant of the need to predict rare events. And as if everything above were not hard, doing it for a rare event makes it even harder. But again, the reality is that when we're talking high consequence applications, we're talking decisions where people's lives are at risk. And for example, in an engineering system, any component in the system that has some aspect that might relate to human life, for example, a flight critical system on board an aircraft, needs to be certified against a probability of failure of 10 to the minus 9, 1 in a billion. And so clearly this puts huge demands on the methods that we need to use. And then finally, again, a point I've already made, uncertainty quantification is so incredibly important. It's very challenging, but again, in computational science and the field, the last 10 years have seen a huge amount of progress on rigorous methods for validation, verification, and uncertainty quantification that really start to drive us towards predictive science, towards the idea of not just being able to make a prediction, but actually being able to certify that prediction and start to put confidence or error bounds or uncertainty quantification around, especially as we go in regimes beyond where we may have data. So again, when we talk about scientific machine learning needing to combine data-driven learning with physics-based models, it's not just the physics-based models. It's all of the foundations of computational science that come with that and that let us take on those complex problems. Again, overcoming these challenges requires more than just big data, more than just black box sampling. We really have to bring to bear everything we know about the system, the mathematical structure that brings, and then the scalable, high-performing algorithms that sit on top of that. Okay, so in the next part of the talk, again, I want to dive in and just give you one example. It's one example from my own group of work that we are doing that sort of follows along these ideas of bringing together data-driven learning with the foundations of computational science and physics-based models, and show you how that lets us tackle a complex problem. So again, I've talked about physics-based models, and I've come to appreciate that this is a term that a lot of engineers and mathematicians and scientists use, and many folks who don't work with physics-based models may not even fully know what it is that we mean when we say a physics-based model. So what is a physics-based model? It's a representation of the governing laws of nature. And what's so incredibly powerful about a physics-based model is it innately embeds the concept of time, space, and causality. So in solving this model and solving the governing equations, we are taking a vast solution space, an otherwise infinite dimensional solution space, and we are defining low-dimensional manifolds on which the system's behavior lies. We're constraining predictions to lie on these low-dimensional manifolds, and those manifolds are defined by the laws of nature. As I already said, these models often come in the form of partial differential equations or systems of ordinary differential equations. Here's one example. This is an example of a physics-based model that represents the reacting flow inside of a rocket engine combustor. And the details of the notation are not important here, but sort of looking at the model from a distance, what you see is that this model is a mathematical representation of the conservation of mass, momentum, energy, and conservation of chemical species inside the rocket engine. And these conservation laws, again, are what define for us how the different quantities would evolve over time, given different initial conditions, given different boundary conditions, given different interventions, and allow us to get some insight as to what's going on. So again, a physics-based model has this predictive capability, and by predictive, what we mean is, given a particular setup, initial conditions, boundary conditions, conditions on the injector, in this case in the engine, and the system parameters, we can solve the model and compute the density, the pressure, the temperature, the heat release. We can compute these physical quantities and predict how they evolve over space and over time. And we can also play these what-if games. What if I were to change the injection conditions? What if I were to change the combustor geometry, again, in order to drive good decisions? So physics-based models are great. You can tell I think they're wonderful. They're powerful, and they bring predictive capabilities. But that doesn't come for free. And here's really a huge catch. Physics-based models are computationally expensive. So for the results that I'm going to show you today, it is a simplified 2D model of a combustor. Even with that simplified two-dimensional model, the kinds of simulations that you can see on the movies here on the left take hundreds of CPU hours to compute. And in terms of wall clock time, they take hours, if not days, for a single simulation. For 3D simulations, I'm not going to show you any 3D results today, but we are also working on three-dimensional simulations. The estimate, we can't even get a full 3D simulation of an entire rocket engine, but the estimate is that if we were to do that, even with massive high-performance computing resources, a single simulation might take on the order of 3 months. 3 months for one case. Now, if we only wanted to do one analysis, that might be fine. We might be able to wait for 3 months. But of course, we don't want just one analysis. We want many analyses. We want to play these what-if games in support of driving decisions. So clearly, the computational expense of physics-based models is a huge barrier to having them be useful in settings where we need to run many analyses. And so that's where the idea of model reduction comes in. And today, I'm not going to present any of the detailed mathematics of model reduction, but rather keep it a high level to give you an idea. So the idea is here. Here on the left, we have a high-fidelity physics-based simulation. So think about that complicated analysis that helps me predict what's going on in the rocket combustor. Again, it comes in the form of partial differential equations, the model. When I discretize it, I get a discretized model that may have thousands of degrees of freedom if I'm in one dimension, all the way up to billions of degrees of freedom in 3 dimensions. And as I've already mentioned, solving that model may take minutes, hours, or even days, or even weeks, or maybe even months. So projection-based model reduction says, can I find a reduced order model? Can I find an approximation of the system that has lower dimension? Instead of thousands to billions, I'm going to look for tens or hundreds or maybe 1,000. And rather than taking minutes, hours, or days to solve, can I solve it in seconds or minutes? And how does projection-based model reduction go about doing this? It does it mathematically. So mathematically, we're going to query the high-fidelity system and look for low-dimensional structure. Again, without any of the mathematics, there are 3 steps. The first step is a training step, solving these high-fidelity models, solving the partial differential equations for some hopefully small representative set of conditions to generate training data. And in the model reduction world, the training data are referred to snapshots, representative solutions. Second, to analyze the training data, analyze the snapshots to identify structure. And in what I show you today, that structure identification step is done with a low-dimensional linear basis. We use the proper orthogonal decomposition, POD, which is essentially the same thing as the PCA, the principal component analysis. So an SVD identifying the linear low-dimensional subspace that best explains the high-dimensional training data. And again, that's what I'm showing you today. There are many other methods, including nonlinear representations that identify low-dimensional structure. And then the third step, and the third step is critical, which is to get the reduced model, we now take the original partial differential equation model and mathematically project it onto this low-dimensional subspace that we've identified in step 2. So the reduced order model is, again, not just learned from the data, but learned from the data through the lens of this original model that we started with, and that original model that we started with comes in through this projection step. So in the way I frame it there, to many of you, you may be thinking, well, it sounds sort of a lot like machine learning with training and structure exploitation. And it's natural to ask, what is the connection between reduced order modeling and machine learning? And in my view, the answer is that there's quite a deep connection between the two, but there's also a number of key differences. And perhaps the biggest difference is the heritage of the fields, where model reduction methods have come from computational science and engineering, CS&E, where we start with an expensive model. And again, we start with an expensive model because we are thinking about mathematical models, these physics-based models, and then the goal is to reduce that high-dimensional model. Whereas in machine learning, which has come from the computer science community, we start with more of a pile of data and think about creating models that explain the data. So the heritage of the models are different, the perspectives are different, but when you really start to dig into some of the mathematics that goes on, and I already mentioned the proper orthogonal decomposition and its connections to PCA, you see that there are actually many common elements. But of course, it's natural to ask, how do we get the best of both worlds? How do we bring the two perspectives together? And what are the best of both worlds? Well, reduced order modeling, I've emphasized a lot the power of embedding governing equations. And while in a reduced order model, those equations are no longer represented explicitly, they are deeply embedded there through that third step, through the projections. So the predictive governing equations sit inside the reduced order model. Second, again, that projection step enables us to preserve structure in the system. And structure is so important for so many reasons, not least of which is structure is a mathematical manifestation of physical properties. And often structure, such as being linear or being quadratic or being stable or being positive, definite, that structure is a representation of attributes that we would like the solutions of our models to have. Third, reduced order models can be predictive in the sense that even though they are approximations, for some classes of problems, it's actually possible to derive rigorous error estimators that give you not just a prediction with the reduced order model, but also let you put estimates on just how wrong that prediction might be, even or especially when you're outside the training data. And I also already mentioned the notion of stability. Again, there are ways in which to do the projection to ensure that we preserve the stability of a particular dynamical system. But on the other side, machine learning has a lot of advantages. One advantage is to discover hidden structure. We know that the physics-based models we work with are often imperfect, and being able to discover and exploit hidden structure without necessarily being constrained by an a priori model is extremely powerful. Machine learning implementations tend to be non-intrusive, meaning that they don't necessarily have to get into the details of a complex code or modify a complex code to be applied. Similarly, they are black box and flexible, accessible and available, sort of all put together, meaning there's a very low barrier of entry, which is very different to the world of model reduction, which has all kinds of complicated mathematics and a need to really interface with these very complex high-fidelity codes. So again, we ask the question, can we get the best of both worlds? And it's this idea of bringing the power of reduced order modeling and the predictive models together with the flexibility and the non-intrusive accessibility of machine learning. And that's what we put together in our approach that we call Lift and Learn. So again, I don't want to, I'm not going to present the details of the mathematics of this approach. You can find that in our papers, or you can email me after the talk. But again, at a high level, here are the ingredients. So a physics-based model sits at the heart. We also employ variable transformations that expose polynomial structure in the model. So rather than constraining ourselves to work with the variables that are used in a high-fidelity discretization, we look at the physics-based model and we ask the question, are there tricks that we could play with introducing new variables or transforming the variables we already have so that our model starts to take on a particular structure? And then third, we use the lens of projection to define the form of a structure-preserving low-dimensional model. And I already mentioned the idea that projection is a mathematical way to achieve that notion of preserving structure. So these three ingredients are really, you could think of them, they're like a thought exercise. They're the pencil and paper part of the approach. And really what these three ingredients do together is they allow us to define the structure of the reduced model. They give us the form, the mathematical form of the reduced order model that we want to look for. And so then rather than taking snapshot data from a simulation code and fitting a black box or an arbitrary, even expressive form of a model, we're going to look for a particular form of a model, and that particular form comes from the analysis that is given to us by the physics. We can do that non-intrusively because we're going to learn only from simulation data, and we do that using the operator inference approach, which is something that Benjamin and I worked on several years ago. And again, without going into the details, what it amounts to is solving a linear regression problem. And we can look at the elements of this problem. So first of all, you can see we're solving the regression problem to find the reduced model, defined by the operators A hat, B hat, and H hat, defined by the structure that define the reduced model. That's what we're looking for. The regression problem is driven by simulation data in the form of these snapshots. That's the X hat. And this minimum residual formulation, which says, find me the reduced model that best matches this form you're looking for in a minimum residual sense, gives you a linearly squares problem. The A hat, H hat, and B hat only show up here. The coefficients are linear. And what's more, this problem has a whole ton of structure. That means it can be solved in a very scalable and very efficient way. Okay, so in the last few minutes, let me show you how this comes together for this rocket engine combustion. And here's what I'm going to show you again is a two-dimensional example where we're considering a single injector inside a rocket engine. So this is a tiny fraction of the problem that we really want to solve. This problem is already extremely complex. So 38,000 cells in the spatial discretization. Again, we've seen the governing equations, conservation of mass, momentum, energy, and chemical species. We are working together with Michigan with an Air Force code that's called GEMS. So this is a high-fidelity, very expensive code that the Air Force uses to study combustion dynamics. We have training data, 2 milliseconds of solution of snapshots generated using this code, and that takes about 400 hours of CPU time. You can see here the very small time steps that are needed to resolve the complex multiscale dynamics. You can see here also the variables that we are using for learning the reduced models. And again, these variables are chosen. They're not the ones that a CFD person would work with. And in particular, you can, if you're a CFD expert, you'll notice that we have too many variables. We're using more variables than we really need. But again, that choice is made to expose this quadratic structure in our governing equations. And then we have test data also that's not used in the training. So one of the first things just that I want to, and I'm going to skip through these relatively quickly, I'm going to tell you something that will not come as news, which is the training data are incredibly important. And in particular, what we see here in this example is we're looking at pressure traces at 4 monitor locations in the combustor. we can see here with just 5,000 training snapshots, just this first half of a millisecond of training data, you can see that it's not nearly enough training data. We can learn a model that predicts the training, repredicts the training really well, but it has no predictive capability. So increasing the amount of training data is perhaps oh dear. Okay, hopefully you guys can still hear me because my computer has frozen up on me, which means I can't. Okay, there we go. Okay, increasing the amount of training data is perhaps the most critical part of getting this scientific machine learning method to work. And you can see that as we go to 10,000 snapshots, you can see that, again, we're able to predict over the training regime, but more importantly, the predictions are getting better. And then as we increase even more to 20,000 snapshots, again, the model becomes better and better in terms of predictive performance. The next thing I want to show you, if I can start these movies going, what you're looking at here is the high-fidelity data. This is GEMS. This is the Air Force combustion code. And then 3 reduced order models, 5,000 snapshots for training, 10,000 and 20,000. And we see here the snapshot that's running through time. And there's 2 things to take away here. First is that pressure is actually relatively easy to get right. Pressure is an important thing to predict, and that's relatively easy to get right. But also you can see that this model up here with not enough training data is just not doing well at all. If I go to the next set of movies, we look at temperature, and you'll see that the temperature dynamics are complex. There's a lot going on. Temperature is much harder to predict because it incorporates all kinds of effects, both from the fluid dynamics and from the reactions. And again, you can see that without enough training data, it's really hard to do well. With these 2 models, with more training data, what you see is, again, we can do very well over the training period. As soon as we start to go into the prediction phase, we're doing reasonably well, but certainly not getting the details of what's going on in the field. So you see here at the final time step, here's the high-fidelity model, here's the reduced order model. Certainly far from perfect, a lot of error here, but you know, we consider this to be a real success in terms of really starting to be a pass down, capturing some of what's going on in the combustor. Okay, so last minute, let me just give you a brief few comments on the outlook. I want to come back to the important point that I made earlier, which is that when we say scientific machine learning must combine data-driven learning and physics-based models, we don't just mean the physics-based models. We mean the computational science foundations that make dealing with physics-based models a tractable problem. And those computational science foundations go back 6 decades, all the way back into the 1950s, where the very first forward simulations were starting to be made. So forward simulations, I talked about the importance of being able to solve multi-scale, multi-physics complex systems, scalable optimization and inverse problems, uncertainty quantification. All of these have a really important role to play together with scientific machine learning as we think about a future of computational science where we really start to harness the explosion of data. And that diverse future of computational science absolutely has to be supported by flexible, accessible languages and programming environments. And I wanted to mention that what I showed you today with the combustion work was all in Python, and I'm sorry to JuliaCon for that. But we do certainly use Julia in my group, along with Python and also the ROS for different applications, and I'm showing you a few of those here. But with that, let me close. I think I have spoken for 4 minutes longer than I promised Rantan I would, and I'll be happy to take a couple questions from the chat. Thank you.
Awesome. Thank you, Professor Wilcox. So we have a couple of questions coming in from the chat. The first question is, when you're trying to bring machine learning to a new science problem, let's say you have some science problem that you're simulating, and you're considering bringing machine learning approaches to it, is there a recommended workflow, or is there an established workflow that you have found within your group?
Oh, that's a really tough question. So the short answer is no. I would say every week we learn something more. But maybe just sort of a few general principles. One is, it is so incredibly important to understand the problem that you're working with. I think it's very, very tempting to reach for off-the-shelf machine learning methods and sort of off-the-shelf data, run your expensive simulation codes, generate data, wrap machine learning around it, and hope for the best. And, there is a lot of low-hanging fruit, and that approach can give really impressive results, which is why it's so tempting. But to go beyond that, you have to deeply understand the problem that you're working with. You need to understand the nature of the data you have and its limitations. I think the question of what variables you work with and what data you feed to the learning is absolutely critical. That sits at the heart of our lift and learn approach, the realization that working with the traditional conservative variables, mass, momentum, and energy, does not expose structure in the problem that the regression can exploit. So that's sort of a new way of thinking for a computational scientist, thinking about which variables you work with. And then maybe the third kind of caution is, you saw in the plots I showed that it's actually relatively easy to do very well over training data. And you can get models that give incredibly good predictions of very complex temperature and concentration dynamics over training data. But the moment you venture into a predictive phase, things very easily start to fall apart. And again, that's very, very, very dangerous ground to be on. So all of these are open questions, but again, this is why we need continued work, foundational work at the interfaces that really bring notions like uncertainty quantification, error estimation, and then scalable implementations to bear on the problems.
Right, and actually just a related question that, I mean, if you're incorporating prior domain knowledge into a problem, you also run the risk of over gaming it in some way, right? In that sense, you sort of lose the the idea that you're actually solving a problem. You over game it in some ways. So that's a potential pitfall that could come from these sorts of methods. Do you know how we can avoid that?
Sure. Well, again, so much of it comes back to understanding your problem. The world is filled with vastly different problems, which is good because it keeps us all busy. We hear a lot about using machine learning to discover hidden physics, and for sure there are a class of problems where there are not good models. This is, I think, especially true in biology, biological models. There's a large class of problems for which if you bring too much a priori knowledge, you're right. You could over-constrain the problem and not discover new, potentially better solutions. But on the flip side of that, there are a huge number of problems for which mathematical models are very well established. And yes, those mathematical models are not perfect. They're never perfect. But they are well established and known to be good representations over systems in particular operating conditions. And for those models, and those models are used throughout engineering especially, they've formed the foundations. They literally have built the society around us, the structural models that have designed the chairs that everybody is sitting in right now. So there is a huge class of problems for which models are actually fairly well known. And I think sort of discovering new physics in those situations is, in my view, a wasted opportunity compared to what the power of learning from data could do. So again, it comes back to understanding the problem, really thinking about what it is you're trying to achieve and not just reaching for the latest exciting method that you might be. I think it's fine to try those things, but to really move the field forward, we need to build the foundation.
Right. Okay, so one last question before we close. Does this hybrid approach help in any way to improve the fidelity of describing highly nonlinear, maybe stiff systems? Like, have you had any, for example, like turbulence in fluid dynamics or something? Have you had luck with training or imitating those kinds of systems?
So yes and no. A great deal of our focus, the focus in my group, is in the setting where we have a high-fidelity model that is trusted, that is used by the aerospace industry or used by the Air Force. And our goal is to come up with reduced order models that will get those solutions in a much shorter amount of time. Now, that's sort of just one class of problems. Certainly, as I was just saying earlier, there's problems for which the high-fidelity models are inadequate, and they're to be able to, for example, bring in other sources of information, to be able to bring in experimental data and use it to complement the models, I think is a really important area of work. But again, I would use some caution because I feel as academics, it's very tempting to come up with problems where we have a whole ton of data. We call it synthetic experimental data. And that synthetic experimental data is beautiful because it tells us everything we need to know about the state of the system. And yes, we may pollute it with numerical noise, but that is not the real world. And I really appreciate working with the combustion experts. It's just one example of how hard it is to get experimental data. And honestly, if there were more experimental data out there, then the physics-based models would be better as well. So again, I feel like we have to tread with caution. There are certainly really exciting things to be done in blending together experimental data, physics-based models that are inadequate, new ways of discovering. But we really have to build on foundations and always keep our eyes on the real world and I think be realistic. In engineering and science, the quality of data is just a huge challenge.
And on that note, thank you very much, Professor Wilcox. We will now move on to our next live talk, which is Diversity and Inclusion Efforts in the Julia Community by Logan Kilpatrick. Logan, are you on the call?
Yes, how's it going?
Yeah,
can you hear me?
Pretty good. You could you can start sharing your screen and take it away.
Awesome. Cool, just want to make sure the screen is visible. Everyone can see the slides on the screen.
Yep, I can see the
Cool.
slides.
Awesome. Well then, how's it going, everyone? My name is Logan Kilpatrick. I'm the community manager for the Julia language. And this talk is going to be about diversity and inclusion efforts in the Julia community. So really quickly, the agenda, we're just going to go over some high-level stuff about what's been done in the last year. I'm just going to provide a quick disclaimer, if you will, on Google Analytics. And then we're actually going to dive into some of the data on the Julia Lang website, discourse, the official documentation, Julia Academy, YouTube, and then we're going to talk about takeaways and next steps. So what we've done in the last year, so we're fortunate enough to have been able to launch 3 new Julia Academy courses. People worked really hard. The authors of all 3 of those courses worked really hard and they turned out really, really well. We've actually had 15,000 students sign up for Julia Academy and take a course over the last year. And there's also some additional courses in the pipeline right now, which is awesome. We were fortunate enough, the Julia language was fortunate enough to participate in Google Code-In this past fall/winter, and we supported 212 students through Google Code-In, which was a huge success for us. And then we're actually currently mentoring 25 students through Julia Summer of Code and then Google Summer of Code combined. And then we are also participating in our inaugural year of Google Season of Docs. And that will be right around mid-August. We should be releasing which projects were actually selected to participate in that. And then the last 2 points, we were fortunate enough to be able to partner with Major League Hacking this year for the inaugural year of their MLH fellowship. And I believe there's, I think, roughly 10 students who are working full-time this summer, working on Julia projects, facilitated through MLH and some of the mentors within the Julia community. And then the last piece is we've been able to make a lot of Julia events global, and part of that we didn't really have a choice because of the pandemic. But I definitely think that it's opened a lot of people's eyes, especially mine, to the fact that we can really make, you know, all of the resources and all of the meetups super accessible by having them be online and global to everybody. Sweet. So some really quick important notes before we dive into some of the data and the metrics. So a lot of the information is coming via Google Analytics. I included a link here in the presentation that you can't see because you're just watching, but I'll post this somewhere afterwards if you're interested in looking through some of these links. The disclaimer is take all this with a grain of salt. Obviously, Google Analytics isn't 100% correct. So some of this data might not be 100% correct. And then the last disclaimer is when I refer to this past year, I'm referring to July 28th, 2019 through July 28th, 2020. And when I refer to quote unquote last year, I'm referring to July 26th, 2018 through July 27th, 2019. So this is what the distribution of users based on gender and age looks like for julialang.org. Previously, we were roughly around 12.4% female users on julialang.org, and that's now up to 17.7%, which is awesome. And then the left-hand side of the screen, you can see the age distribution. And the one thing I'd like to point out is that the number of 18 to 24-year-old users, the little blue graph on the far left-hand side, has actually increased in the past year versus last year is the orange graph. This is the distribution of countries in which users are coming from when they visit the Julia language website. So this is the top 35 countries, but actually we have 224 countries in total represented, which is really awesome to see. And I actually double checked because I didn't know there was 224 countries. There's actually only like 195, I think, that are part of the United Nations. So we are more diverse than the United Nations. This is the distribution of users for discourse. And we were previously at roughly 15% female users on discourse. And now we're somewhere around 19.3%, which is, it's awesome to see that growth and similar trends in the age section as well as the previous graph. This is the distribution of users for the official Julia language documentation. We were previously only at 12.4% female users. We're trending somewhere around 17.7, 18%, which is super awesome to see. So for Julia Academy was previously a Julia computing product that was a paid for service that transitioned to be an open source service as part of the greater Julia language community. So we don't have the same 2-year section of data to present. So we're just presenting 1 year, the latest year of data here, and we're at 18.6% female users. Hopefully the next year when we present this information again, ideally we'd actually want to see the Julia Academy data be more diverse than the other sources, given that this is sort of the place that we're pushing new users to get them involved in the Julia community. So for the Julia languages YouTube, we are not using Google Analytics for that. We're using YouTube's built-in analytics platform. I can't confirm as to why these numbers look so much different than in other places, but previously the percentage of female users on YouTube was 4.8%. We're actually trending this year slightly up, but it's only at 5.2. And this could have something to do with the difference in how YouTube versus Google are detecting metrics about their users. I'm not 100% sure, but it's definitely something interesting to look into. And the other important part for this piece of data is that something we notice is that the diversity of our users actually increases during events like JuliaCon. So if you were to look at the last 7 days versus this graph, we actually have a higher percentage of female users in the last 7 days than over the last year, which is, I think, something positive to see. So some quick takeaways. something positive, the Julia community is definitely becoming more diverse based on this data. But the flip side of that is that I think there's still a lot of work to be done. So the next steps, what do those look like? Today actually is the BOF titled Moving Forward on Diversity and Inclusion in the Julia Community. That's led by Huda in August, and the time is listed there. I think it's the second BOF today, and you can join that on Discord. But if you are watching this video afterwards and you can't join that BOF, then feel free to send an email to diversity@julialang.org or join the diversity channel on Slack. We're always looking for people to help out because as the abstract of this talk was titled, it really does take the entire community to push these initiatives forward. So we need everyone's help on this. And that is all I have. So if there's questions or comments, you can ping me on Discord, Slack, via email, or if there's any live questions, happy to take those. Otherwise, I'll yield my time back.
Well, thanks, Logan. So I'm just looking at the chat, and I guess the first question is, do we have any information on, let's say, racial data within the community, or there's also a question with regard to whether we have any non-binary gender data. Is this something that's easy to collect? Yeah.
That is a good question. I think we would have to, later on during JuliaCon, you'll be able to watch the results of the Julia Computing user survey. And I think that will shed some light on it. And I actually think that's a super helpful metric to get an idea of what our users look like. But I don't think that's something that's easy for us to attain automatically. We really have to rely on those manual surveys like Julia Computing did to get that data.
Right. Well, on that note, Logan, thanks very much. And we'll move on to the next set of speakers.
Thank you.
Who will be talking about Juno 1.0. And our next speakers are Shuhei Kadowaki and Sebastian Fitzner, who will be talking about Julia 1.0. Whenever either of you guys are ready, feel free to share your screen and start. Yeah, I can see your screen. Yeah, Sebastian. Sebastian, are you speaking right now? Because I don't think I can hear you.
Can you hear me now?
I can hear you now. So
Yeah,
would you mind
okay.
restarting? Yeah.
Yeah, sure.
All right, thanks.
So it appears my webcam is broken again. Sorry about that. Anyways, I'm Sebastian. I've been maintaining Juno for the last few years, recently joined by Shuhei. And today we're going to announce Juno 1.0, or will we? Actually, this talk is going to be about the Julia extension for VS Code, and we are announcing version 1.0 of that. This talk will have contributions by David Antoff and Shuhei Kadowaki. So yeah, let's get straight into it. What's going on? Well, the Juno team has decided to join David and Zach, the two main developers of the VS Code extension, about 2 months back. And our future efforts will focus on languageserver.jl and the VS Code extension for Julia. This means that by now Julia for VS Code is almost at feature parity with Juno. It also provides linting and more static analysis features. So at the end of the day, it should be more powerful than Juno. We've also tried our best to make the switch from Juno to VS Code as easy as possible. And we hope that users of Juno will feel at home in the VS Code extension. Why are we doing this? Well, Juno is built on Atom, And Atom's development has slowed down tremendously over the last 4 years, and even more since GitHub was acquired by Microsoft, and Microsoft has poured more resources into the development of Visual Studio Code. And the Juno developers, Shuhai and I, we think that VS Code and the language server protocol, which powers the extension, are the future, basically. There are also additional benefits to this, because we don't need to re-implement any more static analysis features for Juno, which already exist in the VS Code extension. For example, proper static linting. And also work on language server.jl will benefit the whole editor ecosystem. There are front ends for Emacs or Vim or Sublime Text that work with the language server. There are also a few design problems with Juno. For example, Juno's whole backend is running in the REPL process, so that will create issues with code loading, stability, and Julia environments, because we can't control what the user's running in the REPL process. So they might inadvertently crash the whole editor experience, for example. VS Code, on the other hand, only involves the REPL process when that is absolutely necessary, and does everything else in another process. Changing to that implementation for Juno would be a fair bunch of work. So it's nice for us to build on the work that David and Zach have already done for the Julia extension for VS Code. Now, as to Juno's future, Juno is in maintenance-only mode for the last 2 months or thereabouts, and we've been fixing bugs that we either deemed critical or that were easy to fix, but we decided to stop implementing new features. That said, Juno is still completely usable. There's no reason to switch right away, but we will only implement new features for the VS Code extension. The last point in this introduction here is the question of a name. If any one of you knows a good name or can think of a good name, then feel free to contact us with any suggestions you might have. I've jotted down a few rough criteria there, but those aren't set in stone at all. Right. Let's just look at the new features. The VS Code extension has gained since last JuliaCon, and the fairly big thing is the debugger. There are already some debugger implementations around, debugger.jl and the Juno debugger, and now the VS Code debugger, which are all Julia interpreter based. Infiltrator and mixed mode debugger are two more experimental debugging-like experiences. I'll just let David show a quick demo of the debugger here. I hope you can all hear him.
So here I am in a standard Visual Studio Code window. I'm going to open this file here. It has two functions defined, foo and bar. A bar is calling function foo, and then in the global scope here, I'm calling function bar. To run this script inside the Julia debugger, the easiest way to do that is to click this button here, debug Julia file. You could also press F5 on your keyboard. And that will start a new Julia instance and run the content of the currently active Julia file in that Julia instance. You see the output here down in a terminal window. So this run was not very interesting because everything worked out. So I'm going to close the output window here. And now we're going to run this again. But this time I'm going to set a breakpoint in the function foo. I set the breakpoint by clicking here in the left column of the text editor. And a little red dot appears here. So now I'm going to start the same file again. And this time execution should be paused, or we should jump into the debug mode as soon as the code reaches this line here. So we now broke into the debugger. You can see that the yellow line is the next line that would be executed if we continued execution of this code. Here on the left-hand side, you can see the local variables in this function here and the values that they currently have. So now I'm going to step over this line. I can control stepping up here in the toolbar. So I'm going to say step over, and then I'm going to step over again. And now we've defined a new local variable C, which now appears here in the local variable list. So I can step again. So the next expression is interesting because what I'm defining here is an array of pairs. So this is a deeply nested structure. So the variable D is now shown here as a local variable, and I can drill down into it. So I can see the three different array elements that I have here, and then I can drill down into each individual element to see the fields of each of these pairs here. So you get a rich UI to look at the runtime values of structures here. I want to use my final seconds here to show you another way to start the debugger, and that is from the Julia REPL. So I'm going to start the Julia REPL here. I'm going to run these function definitions in the Julia REPL so that they are defined inside the REPL. And now I'm going to say run bar inside the REPL. And that will run the function bar inside the REPL process, but inside the debugger. And we should actually break at the line where we set the breakpoint again. And that concludes my very short demo of the debugger.
All right. Then the next big thing that the Juno extension has very recently gotten are inline results and a working workspace pane. Both of those are probably familiar to Juno users. And the inline results are opt-in, but if you're coming from Juno, then I'd heavily recommend you to enable them. Shuhei will give a short overview of what that looks like in VS Code.
Inline evaluation enables Reaper-like interactive coding environment. It automatically selects current code block, which is an unit of code for evaluation. So if we have this macro, we can simply place a cursor anywhere inside of it, and then execute it. Result bubble will pop up, and we can get instant feedback as in repo. Hovering over the result will get us more details. So we can see the analysis result of code typed function, like this way. We are also supporting cell-based evaluation, as in Notebook. These two subsequent steps are the cell delimiter, and we can evaluate the code between all by once. In the case we hit an error, the backtrace will be highlighted with red lines. We can get details of the error by hovering over any of those lines. And we can go to whichever stack frame by clicking any of those links. We can also use these topmost utility icons, and the leftmost one will navigate you to the deepest stack frame. The error occurs. And the rightmost will clear all the highlights. Let's look at this status bar item. This is the current module indicator. It is now indicating main module, because these random pieces of code don't live in the package. But if we switch to a file that lives in a specific module, it is now indicating a base module. This means the code at the cursor will be evaluated in the context of this base module. So module macro here returns base, and if I have an ad hoc change so that these functions don't error on empty any typed collection, now the code doesn't error. So as you can see, our inline evaluation actually provides the equivalent feature as revise and can be alternative for it. Lastly, let's click the Julia icon on the activity bar. This is the Julia workspace view. Workspace view contains every object in this running session. So there are those macro and function I have defined so far. For demonstration, here is an example code adapted from Zygo. It is now wrapped in Zygo demo module. So if I execute this file, Zygo demo module will pop up here, and we can inspect into it and see what it defines. We can also inspect into structs and arrays and dictionaries. These drill down are lazily computed, so we can inspect into however large arrays or even a recurring objects without any editor performance problem. So as a summary, inline results are very useful for scripting or inspecting code. Automatic module detection helps you develop a Julia package with the Canvas-style programming in a deviceless workflow. Julia Workspace View will provide you useful inspections about your Julia runtime.
Juno also has a profiler, as those of you who use Juno will know. We have also implemented an experimental feature into the VS Code extension that makes use of another extension that you can see here on the right to show flame graphs of the output of Julia's profiler. This isn't quite ready for prime time yet, but the current release of the extension already includes all relevant functionality. So feel free to give it a go and play around with it a bit. Just be aware that some parts of the display mechanism might not quite work as expected. Another nice thing that both Juno and VS Code have is remote editing. Juno's remote editing was a bit ad hoc and cobbled together from multiple pieces of code, whereas remote editing experience in VS Code is very stable, thanks to this plugin you see here on the screen. I'll just give a quick demo of what that looks like. As you can see, I'm on a Microsoft Windows machine here. And with that SSH extension, I can run code on a Linux machine, as you can see indicated in the lower left corner, and also in that terminal there. Plotting works just fine, and debugging works just fine. In short, all of the VS Code extension's features should work the same on a remote machine as they do on your local machine. This is especially nice when you are running some expensive computation, potentially need a big GPU or something else you might not have in your laptop. Then you can just SSH into a cluster or into another powerful machine and run your code there without any change in workflow. We've also made some changes to how the release process for the Julia extension for VS Code works. We switched to basically continuous delivery mode, and David will show that now.
One other thing we changed in the last year is how we ship the Julia extension to our users. We now have the concept of an insider channel and a release channel, where we have a smaller group of users on the insider channel that help us test new versions of the extension before we then ship them to everyone. The way this works is that we very frequently tag new versions that we ship to the insider channel. Essentially, whenever we've added a few bug fixes or a few new features, we will tag a new version. We then monitor the quality on the insider channel from our crash reporting. And whenever we have a build where we do not see a regression in terms of the crash reporting, we will ship that build to everyone. In practice, the way this has played out is that we often tag new versions for our insider channel every single day. And then the majority of those builds typically goes out to the release channel so that the extension is often updated once every day.
All right. Those were the big things the Julia extension already has. But of course, we have also plans for the future. Now that all 4 of us are working in the same code base, yeah, let's see what's in store. Shuhei is working on a pull request to implement a documentation browser, just like the one in Juno, and some more dynamic features. So let's see what he has to say about that.
As a future enhancement, we are planning to support a documentation browser. With the documentation browser, we can see a documentation on an arbitrary symbol. We can get local documentations, as well as a documentation in the package. As it appears, it uses Documenta Julia's styling, and LaTeX renderings and syntax highlighting will be enabled. We are also trying to support link handlings and browsing back and forth navigations. I'm also working on bringing more Juno-like dynamic features into our extension. A simple example would be this property completions on global objects. Which is actually very hard to do within the static analysis of our language server. Another example is method signature help with dynamically inferred return type suggestions. For this example, the return type of this function call gets inferred. This is done by Julia's type inference system, using the input arguments on the fly.
Another nice upcoming thing is complete notebook integration. That's still an experimental feature in VS Code, but as soon as it's released, we'll also have Julia integration. David will show the work in progress PR now.
We are currently working on native notebook support inside VS Code for Julia. Here you see a preview build where I have opened a notebook file and it mixes markdown cells with code cells. I can easily run these code cells and see the output in line here, as you might have experienced that in other notebook systems. One benefit of having this inside VS Code is that we integrate with all the other features that the extension provides. And so I think at the end of the day, this will be the richest notebook editing experience for Julia. For example, if I write code here, I get full inline completion support, I get method signature support, I get Hoover help for the documentation. I am very confident that we will be able to add full integration with the debugger before we actually ship this feature, which I think will be a first that you can debug Julia code inside a notebook.
There are also some problems with the current VS Code extension, but we do have plans to work around those. And again, David will tell us about that.
There are 2 areas in the core Julia language support that we want to focus a lot of efforts on in the next couple of months. The first one is support for multiple Julia environments per workspace. So currently, you can select one Julia environment per VS Code window, and then all names, symbols, resolution, and so on in the IDE happens within that, in the context of that Julia environment. That doesn't work well with things like specific dependencies for test folders and in doc folders and so on. And so we hope to fix that by adding support for multiple environments per VS Code window. The second thing we want to focus on is indexing of packages. That currently is still too slow. And our hope is that we can move the indexing of any package that is actually tagged in the public registry into the cloud so that it doesn't have to happen on your local machine at all. And we hope that that will significantly speed up that part of the extension.
Documentation for the extension is also another big thing.
We also hope to greatly improve the documentation for the extension over the next couple of months. We are very aware that, well, it's not even fair to say that the documentation is not very good because it just doesn't exist at all for the most part. So what are our plans? So the first thing is that we will go from this horrendous homepage that I designed at some point to this much nicer homepage that Sebastian created. So that should be live right now. That, of course, is only optics, but we also are going to apply for the Google Season of Docs program. We actually received a very large number of very high quality applications from students that want to work on our documentation. And I hope we will be successful and get someone approved. And in that case, there is real hope that the documentation for the extension will improve greatly over the next couple of months.
All right, so in summary, the Julia extension for VS Code version 1.0 should be out now. We tagged an insiders version yesterday, and I think David has, or might have tagged the actual release during this talk, or at least will soon. Your feedback is very welcome on GitHub, Discourse, Slack, or wherever else you can reach us. And yeah, one more thing. On Friday at 4:10 p.m. UTC, there's going to be another talk about using VS Code for Julia development. So be sure to tune in then. And yeah, I think I have some time to take questions now.
Well, thanks, Sebastian. It looks like you guys are doing a fantastic job of answering questions in the chat. So I'm actually combing the chat to see if there are any outstanding questions. So there's a question about weave integration in VS Code. Can you comment on that? What the state is, etc.
Yes, so basically weave integration as it is in Juno will be subsumed by the notebook integration that David has been working on. We don't need to use the Jupyter notebook format for that. We can just as easily ingest weave documents or even literate documents and evaluate those via the notebook UI.
Great. And one last question. Are any of these amazing efforts that you're doing for Atom and VS Code, sorry, for Juno and VS Code, do you think any of it will bleed on to other editors like Vim or Emacs?
So in theory, the whole backend part of it, everything that's happening on the Julia side, will be usable from other editors that support the language server protocol. I know that Vim and Emacs do. Sublime Text also, I think, has a support for that. And yeah, all of the work we are pouring into the static analysis features and so on will be available from those editors as well, yes.
All right. Thanks, Sebastian. And on that note, we will move on to our sponsor talk for this live session from Julia Computing. So take it away, Matt Bauman.
Hi, everyone. Thanks so much for being a part of this, and thanks for all the participants and all the speakers. We at Julia Computing are just thrilled to be sponsoring this event and thrilled to see all the engagement and talks that it's creating. It's just really, really exciting to see what's happening and see all the great developments throughout the Julia ecosystem. My name is Matt Bauman. I'm talking on behalf of the company here, founded by the 6 folks that you hopefully can see on the left there. Our company has been growing like gangbusters. The 2019 company shot there is on the screen, and there's now about 40 of us. So we continue to strive to do great things. I just have 5 minutes here, but I have some really exciting things to share with you, so I hope you'll stick around for it. At Julia Computing, we work with enterprise customers and companies to try to help make them use Julia as effectively as possible. This takes the form of a bunch of products that we have and has allowed us to work with some really cool companies and work with some folks doing really amazing things. In particular, I'll talk a little bit about Julia Team and Julia Run. That's what allows you to use private packages really nicely. But for the most part of today's quick thing, I want to talk about Julia Hub, which hopefully all of you know and recognize and have been to. If not, I encourage you to check out juliahub.com. We see that as your entry point into Julia and the center point of all Julia development. So you can browse documentation, search through the repositories, see what's there, see what's available, and even register open source packages. But there's a missing piece here in our eyes, and that's getting code running and making code run well. And so I want to demonstrate some upcoming functionality that we're going to incorporate into Julia Hub to launch code in the cloud. And to do that, I want to lean on AlphaZero. And AlphaZero is this really cool machine learning framework that combines learning and search to solve complex and arbitrary problems. And it's started from the game of Go, which is this crazy game with so many complex trees and things to search through. And AlphaZero solves this by leaning heavily on compute. And in Julia, we are so fortunate to have great contributors to the ecosystem like Jonathan Laurent, who we've been working with for the past 2 weeks to help deploy AlphaZero on the cloud. And AlphaZero.jl is his package that takes the work and makes it simple, extensible, and fast, and kind of is an awesome learning platform to understand how AlphaZero works. And it's extensible using Julia's great generic interfaces to allow you to play with new games. You can see in the logo there, it's not just for Go anymore. There's chess, tic-tac-toe. We'll be demonstrating Connect 4. And of course, since it's all leaning on Julia, it's understandable, well-documented, and fast, between 1 to 2 orders of magnitude faster than any other high-level alternative. Traditionally, AlphaZero implementations have been written in C++ or C or other hard languages, and very tied to their distributed, code mechanisms, because you have to do a lot of compute to get an agent trained up. Well, AlphaZero uses all of Julia's great parallelism tools, including distributed, multi-threading, and GPU parallelism to get the most out of all of your things. So you can run this today on your desktop computers, and it'll take about 12 hours or more to train a good Connect 4 game player. And we want to show this and get this parallelized on the cloud. So let's look at what that looks like. Here we have Julia Hub in an internal release that has the run on cloud functionality for up and running. You can see I can add Jonathan Laurent's package here, and a run in cloud button appears. I can click that. You can see it already knows the project and manifest, so it knows exactly what code to send out to all the workers. I can additionally tweak parameters right here in the web UI, or I can select a particular branch to run off of. I have all the parameters coded up the way I want them to be on a particular branch here, so I'll choose those. Now here comes the fun part. You can pick your cluster to your heart's content here. How many nodes, how many threads, what you want to use. In this case, we want to use GPU nodes, right? So we can pick a beefy GPU to use, grab 11 nodes and hit start. While that's starting, I can point out some other things here. We have some time or cost limits to make sure you don't go over budget as you submit your jobs. And there you go. You can see that we've successfully submitted our job. Now it'll appear down in this bottom table where you can see exactly what we ran, what our inputs are. You can have a place for outputs, or you can even just watch the logs roll in live and see them start coming through. This is a little abridged because I only have 5 minutes, but you can see it's starting to learn and starting to grab the loss and iterating here. And so that is AlphaZero doing its thing on the cloud. Now, that's just half the story, right? Getting code up and running in the cloud is great and all, but you really want to introspect the results and see what's going to happen. So let's switch over to VS Code, of course, right? And while Sebastian's been working on all of the things there, he's also been working on an interconnect to Julia Hub, where we can download the results from a run. From there, you can see the job list, and I'm just going to untar these results into my local namespace here. And AlphaZero has built into it some really cool tools for learning and introspection. So we can go to the file browser, pick out some of the plots that it generates. There's lots of depth here and lots of ways of exploring how AlphaZero does its thing. Encourage you to check that out. Let's just look at the benchmark of what percentage of wins did we have on each iteration after each training. And you can see after about 5 iterations, we are getting pretty good agent. It's even more fun though to see what happens as you run your scripts and do this as you go. So you can run AlphaZero, run this agent and play a game against it and just kind of watch it, choose what to play, choose which positions to go. And you can see here exactly what it recommends, and you can decide to follow that or do something different. You can even play blind against it. At this point, I believe AlphaZero will never lose. This is a relatively simple game that it can learn and understand pretty quickly. And this only took 2 hours to train. So whereas it would have taken 12 hours on a single desktop, this only took 2 hours because I was able to distribute it across 10 workers. So this is all very exciting. But now I've introspected it. Let's change something. So we can change some aspect of the neural network. And we can resubmit a new job now without even leaving VS Code. We can go in here, pick up, design our cluster, figure out exactly how we want our cluster to look. Say, oh, yep, we want to use GPUs here, pick out our 10 workers, get this all set up and hit start. So we see this as just a huge leap forward in how you'll be able to scale your code. And there's just one more thing. This actually wasn't running in VS Code. It was running in Chrome. And this is one of the really cool things that VS Code enables is that there's, we can run this code in the browser on a remote machine. And so we just see this as a huge, huge, huge leap forward between all the great work in VS Code plus the ability now to deploy on the cloud. We want you to sign up and get on board. We don't have this public yet, but we're going to start launching this to early access folks. So I demoed here in this quick 5 minutes was compute on Julia Hub and connect to it via VS Code. So check that out, follow that link, register your interest, and we'll be in touch. Now, Julia Hub is powered by Julia Team and Julia Run. You can learn more about how this works and how the same architecture can be extended to work with private packages, registry management, get things running behind firewalls, behind air gaps, provide governance and security that you need, and even connect into on-prem clusters. So I'll be demoing that today, tomorrow, and Friday. A lot more to cover here than I can possibly do. So encourage you to sign up for those, juliacomputing.com/events, sign up for one of those slots, or register your interest in the individual user Julia Hub. So thanks everyone, and have a great conference.
Thank you, Matt. That was a great presentation, and we're really grateful to have Julia Computing as our sponsor this year. On that note, I think we are done with our live session. Avik, feel free to kill the Zoom call at any time.
Thank you, everybody, and enjoy JuliaCon. Bye-bye.
Yeah.